Okay. So welcome to Math 684, Scientific Computing with Python, or summer. Those of you who are taking this class remotely, and those of you who are in the room. Those of you who are here. Now, is it going to be a problem to get here by 10:45? I just need to know. So are you coming like directly from the zone, or? Oh, okay. All right. Okay. So I just need to know. It doesn't really matter to me, but okay, just so I know when to expect people. Well, we have 10 people in the class, and there are only 4 people here. I thought there might be 1 or 2 more, but well, we'll see. So wondering where Sabagi is. Okay. Now, so here's the site like I usually have for my classes. And so a quick rundown for all the usual things. That this is now I'm not assuming prior Python knowledge. We will spend time at the beginning on the basics. Some of you may have dealt with Python in another class because we have, for instance, none of you in the room were here as an undergrad, but some people in the class were. They've taken like Math 305 that got some Python exposure. But the real goal here is that everyone in the class has done some amount of either coursework or research or both using Matlab. And the idea is that by the end of a semester, that tasks that you're already familiar with in Matlab, you can just as easily do in Python. So that you can legitimately put on your resume or CV that you can work with Python like you can with Matlab. And in particular for numerical analysis applications. So the NumPy and SciPy packages will be using functions from those, particularly NumPy. That'll be used constantly. That has routines to perform MATLAB-like tasks, like solving systems of equations, linear or nonlinear, or differential equations, matrix operations, things like that. So all fundamental numerical analysis tasks. As far as materials, I'll be posting various resources on the site. I'll go over there after I finish discussing this page. My textbook with Amber Sumner numerical analysis as a reference for the mathematical techniques that we'll be working with. Some of your assignments will deal with implementing certain selected algorithms. It's like standard numerical analysis algorithms, like adaptive time stepping for ODEs, things like that. So for that material, we use that textbook as a reference that I sent to all of you. So that's the version of a book that's actually supposed to be published. So nobody posts this on the web. Burn after reading. I think I have some Python books at home that are pretty good. If I can find them, then I'll make you aware of them. if they're good. Well, they might be too old though. Those of you who have any familiarity with Python would know that there's Python 2 and Python 3. This is a Python 3 class exclusively because Python 2 is kind of like on its way out. So just to clear that up right away. So as far as how your grades can be determined, well, this is a programming class. It's all about how well you can code. I'm not giving tests or written homework problems, or I'm not going to quiz you on like Python jargon. It's all about the code. So we'll start. I may not, depending on how quickly we move along. I probably won't give an assignment this week, but if not, then definitely next week. We'll start out pretty small and just ramp up in complexity from there. Now, so since this course spans June and July, the idea in June is to take care of everybody's fundamentals, make sure they have essential Python skills enough to implement substantial things, and be able to implement typical numerical analysis tasks in Python. And then what I'd like to do during July is have you guys work on some more substantial projects, which may include putting pieces together from prior assignments. And as far as, so you can think of it as having like a final project in a way, or it could be more than one. But I want to make this class, especially the second half of it, flexible in that respect. So what I mean by that is, for more substantial projects that I'll have you guys do during July, I will come up with like default projects that you can do, or if you are research active already and there's something like maybe relevant to your research that or for those for a couple of people for that this applies to on a job that you'd like to implement in Python, then go ahead and talk to me about it. And so we would agree on what the specifications would be, what the scope of it would be, and keep in mind time frame is important. It has to be something that can be done by the end of a semester. So toward the end of July 26th is our last class meeting. So now we'll talk more about that as we get closer to the end of June. But if you'd like to actually do some of your research coding in Python, then that's something that can be a project for this class. Because of that, I want to make sure that the class is as relevant to each of you as possible. Okay. Now, as far as resources are concerned, well, now I don't have anything yet on this page. I will be adding things as we go. In particular, any Python code files, so .py files that I use during class, I will post after class. So you can go here like the next day or something and find them. I'm not sure if I'll have any reading. It depends on if I find any good Python books, or I might have them on hand already. But so I have that column there just in case. I also want to make you aware, I'm away at a conference during early July, so I've marked these 3 days where I definitely will not be here. But what I will do while I'm gone is I will record something, for presenting whatever material, or I'll also use that time to answer any questions that I've gotten. For instance, if someone emails me a question and I think that the whole class would benefit from the answer, then I'll record myself answering such questions. So while I'm gone, as much as possible, the class will continue, and I'll post things as we need. But what I'm hoping is that by the time we get to July, that each of you has a big project in mind, and is off and running with it. As I mentioned in my initial email to the class, classes in June might be disrupted if I'm called in for jury duty. It hasn't happened yet, so I'm glad that I can at least be here on the first day. So I have to call every night and find out if they need me the next day. And so if that happens, I'll shoot you an email about how we'll handle class. Probably what it'll be is I would come here in the evening, record what I was going to present, and post that. So we'll try to minimize disruption, but disruptions there will be. Okay. All right. probably the most important page of the site right here, the resources page. All kinds of things to download. Now, this first link is just having Python by itself. It comes with a sort of a default development environment, IDLE, or idle, and you're welcome to use that. But by default, it does not come with the scientific computing packages like NumPy and SciPy. Those would have to be downloaded and installed separately. And I do have a link for that here, where you can actually go to scipy.org and download things. But will be easier. This is what I'm going to do for my own purposes in this class. Is just get Anaconda. All of the stuff on this page is free, so there's no issue. That's one of the main reasons people like Python compared to Matlab is because Python is free and Matlab is not. Although USM just purchased a Matlab site license at great expense to them. So
just recently, right?
Yeah, I was in the meeting last semester when we talked about that.
I found that. I'm like, how long has that been up there?
So university shells out about $20,000 a year, so that what?
That's a fair amount.
Yep, and every person in the USM community can use it, and presumably can use it off campus too. I think that is taken into account, and also we get several toolboxes that are included. I think generally the ones that we'd like to have. I don't know which package they got, but so that's no longer part of the equation for USM people. But like for instance, one of my closest colleagues, Patrick Godati from UC Irvine, a few years ago he switched from Matlab to Python. So now I have to decipher his Python code, and now that I'm teaching his class, it's a lot easier for me to do. But he's just one example. There are many people in the numerical analysis community that are making this change, and that's one reason why I wanted to run this class. Students who are in the process of applying for jobs are saying that employers want to know if they know Python. It's of great interest to them. So when I went ahead and installed Anaconda, that includes of these packages like NumPy and SciPy already, and it has a nice development environment included called Spider. So all right, so just checking among the people in this room, but that's only half the people in the class. But how many of you have already installed something for Python? Okay. Oh, you all have? Okay, great. If I go ahead and launch Anaconda, so if you're watching this and you haven't done that yet, you need to. So pause the video and then get all that installed. Now, I want to make sure. Now, the thing is, I'm working on a Mac, but I know some of you are on Windows, and all the stuff is available for either one. But I want to make sure that everybody is able to follow along, particularly those of you who are here now. So when you launch Anaconda, it's an Anaconda Navigator. Now, in this class, since it's an introductory Python class, I'm going to keep things simple. There are a lot of features, a lot of things that could be taken advantage of that I may not necessarily get into. The main thing is to be functional with Python. So what I'm going to be doing habitually is going to Anaconda Navigator and launching this, Spider. And that's where all the work can be done.
And where did you do that at?
So this appears in the Anaconda Navigator. Okay. right. Now, I wonder if I can zoom in here or something, because like what that looks pretty small on the screen. Let's see if I do a default zooming in the Mac. Nope, that doesn't work. Okay, maybe it'll let me like change the font size. Ah, okay. Yes, it does. All right, so. Okay. Is all that readable for you guys, especially in the back of the room? Or should we make bigger? Or
I think for recording, you might want to make it larger than 20 font. I know
Yeah.
it'll take up just so much space on the screen.
make it so the little.
Larger, at
Yeah.
least 20
Yeah.
point font.
Okay,
Maybe
let's
larger, but
try that.
anything lower than that really would be very difficult.
Yeah, because I'm also concerned about like some of the text colors that they use here. Let's try 20. Oh, moving up front. Well, we definitely have plenty of room here. Okay. All right, let's try this because this is similar to like when I'm not connected to a projector. Then this is how it just looks on my screen normally. Yeah, because I'm looking at this here. It's like, oh my god, that's way too small. Okay. Now, so when you launch Spider, then this is the environment that comes up by default. So over here on the left is where you can create code files. So similar to M files in Matlab, these would be .py files. I'll just call them Py files. So it's created a like a temporary untitled one here, but I'll be opening various ones as we go. And then we have our console. This is kind of like the command window in Matlab. So this is where you'd actually type in Python commands, which could mean running Py files or performing mathematical operations, things like that. So I'll be typing largely in here, and then we have a help console. But you can also get help in the console window itself. So what I'm going to do is I'm actually going to close this because then there's other things that come like Variable Explorer, but I don't have any variables yet. There's also a File Explorer. I don't really have much in this directory. I'm going to change my directory to where I have all of my Py files that I worked on. So I've been busy lately writing a bit of code. Some of this is for your first assignment, so I'm not opening all of these. But it makes it easier for me to help you guys with them. Okay, and then but some of these you'll be seeing a little bit later. And so I'm going to close this. Okay, I want to close all those things because now this window is made bigger. Because I like you to be able to see more of whatever commands I'm typing in here. Okay. All right. Okay, so the other thing I want to mention, just for those of you who are here, so this class period is 2.5 hours, 10:45 to 1:15. There's no way I'm going to stand up here for 2.5 hours straight or expect you guys to sit there for 2.5 hours straight while I'm going through stuff. So the way I'm going to structure it is roughly break this down to there'll be 3 40-minute periods where I'm actively doing things, or actually doing things together, with 2 15-minute breaks in between. So what I'll do, so normally what it would mean is I start at 10:45. And then our first break will be at 11:25, which is 4 minutes away. But we started late. So I'll just get a few things going here. Now, so what I'm going to do to start with this, and I don't have any particular expectation as far as pacing is concerned. The goal is that all of you, especially those of you who are here now in the room, are able to follow with what's going on, and are not left behind. At least there's only 5 of you. Well, there should be 6. So, so I'm not really big. Unlike my other classes, I don't really have a schedule laid out up front. I do have certain things I do want to get through, and I'm confident that within a few weeks we can. So, I have no vested interest in rushing through anything. So take advantage. Now, what we have up in front of you now is this is the textbook I sent. So my numerical analysis textbook that I'm using as reference for certain things. Now, the book is written in a way that caters to Matlab, and at the beginning is this big long section, 30 pages long, of a Matlab tutorial. So, since a major goal of this class is that all of you who are accustomed to performing certain tasks in Matlab want to be able to do the same in Python, that's what we're going to do. Is we're going to go through the various tasks that were done here in Matlab, and we'll step through how you perform similar operations. And for just about everything, not everything, but almost everything, there is a counterpart in Python, so that you can also see the differences. But one resource that is very helpful for making the switch, or a couple of resources for making the switch from Matlab to Python, are these web pages here. So from the SciPy site, there's this page that's all about NumPy for Matlab users. With NumPy, you have variables that are like ND array for, I'll make this bigger here, an ND array, or another type that's called matrix, and which should you use? In this class, I'm going to use ND array, and this is following their recommendation, their short answer here: use arrays instead of matrices, because anything you need to do with a matrix, you're able to do with these ND arrays, all the essential matrix operations. There are some reasons for which people like to use Python's matrix type. So it's not useless or anything, but that's why there's a long answer here. So there's actually a lot that goes into differences between MATLAB and Python, like all these different equivalents, and unfortunately, there are some things that they left out, unfortunately. But you can see that they've been pretty thorough. And what that page does not cover is likely covered in this other page that's been produced. That's about all the different equivalences. And actually, these pages were very helpful in preparing some of this material for the class, because I'm in the same situation. I've used MATLAB for a zillion years, and I'm wanting to make this jump to Python as well. There are some commands that are exactly the same, but not many. So, actually very few. So these resources can be helpful if you're something you know how to do in MATLAB, you're not sure what the Python equivalent is. These pages can help. But what I'm hoping is that this tutorial will help also. And so what I'll be doing is stepping through these things. I'll be typing everything in the Python window. And whatever I type out in here, each class period, I will post after class. And I'll do my best to include lots of comments. So I'm explaining what I'm doing as I'm doing it. So you can have all that information there too. But occasionally I'll be flipping back and forth between this and the book, because there'll be certain exercises in here that in the book are for MATLAB, but we'll try to do these same things in Python.
Is there like a history or file, script file that you use to capture what you're typing?
There are history facilities. I seem to recall it's rather cumbersome, but actually, I think there was something like because I remember seeing it when I was doing all these things. That it okay. One thing I found to be a pain, unfortunately, compared to Matlab, is logging. Like in Matlab, it's really easy. You just type diary and an optional file name, and honestly, I had trouble figuring out how to do this. I couldn't figure out how to do that exact same kind of thing in Python, but but I figured something. I saw something where it would save your commands, at least. In I think actually I think it's one of the windows here in Spider, where it would have all that. Oh, that's interesting. Spider has a Matlab layout. If you want to do that. Okay, now. And you actually want to check something about the various windows, because like the ones I'd closed earlier. Okay. Okay. Actually, what I'm going to do here is... there it is. History log. So, in order to see it, I had to close the console. So it's one of the windows that's hiding here. And notice, it's writing a file called history.py. So basically, it's a... so in fact, it's a Python script. So if you want to rerun that, you could run it just like any other Python script. So here you're seeing every single thing I've done for the last few weeks. Okay. Yeah, Spider's not making it easy to access this, and I want to find out.
Does it run automatically then?
Or it's saved automatically so that you can run it. But what I want to check on is I want to find out where it saved it. Because, okay, yeah. So there's the history. Okay. So I'm going to go to the directory where I'm working. Okay, because it's not there. Unless it's something where it's not actually saved on your disk yet, but it's here so that you could save it. Okay, I'm gonna do a search for
Maybe you have to find out.
yeah, or maybe I have to actually explicitly. Okay, so here there's history.pys. Oh, but these are like under the installation, so that wasn't me. Okay, and this stuff, yeah. So I'll bet what I have to do. I'm gonna see if it'll let me save this. So I do save as. Oh, it thinks I'm looking at this source window, which it's not what I want. Okay, so, but what I could do. Let's see. What is this? Okay, that doesn't help. Okay. Yeah, I think probably the easiest thing to do would be to, once you get to this window, is copy all this. And go ahead and then you can save it in another. So what I could do is, I could copy all this and paste it over here in my source window, and then save. And then if I use file menu save, that's what it'll save. So the information is available. It's just not as accessible as you might like. All right.
So, like, when we turn in projects, what would we save and turn in this?
What I want to see is your .py files, similar to your .m files from Matlab, and then what I can do is I can just run them. And actually, because we all have the same package and so forth, So what I should be able to do is just take your .py file as is and just run it as if it was on your computer, and everything should work. Okay. Well, all right. I'm going to close this. And now, well, actually, I need a Python console since I closed the one I have. What? Yeah, okay, so I could do that. Okay. All right, yeah. And I want these windows the same size. Okay. So what I'm going to do now is start the. So I have my cheat sheet here, all the commands I'm supposed to do, and start stepping through it. So if you were looking at the books, my textbook's Matlab tutorial, you'll see I'd be stepping through the same things, but there won't be a need to actually look at that because I'll be typing everything in here. Okay. Now, comments, a single line comment is preceded with a pound sign or hashtag or number sign or whatever people call it these days. I don't even know anymore. What?
Octothorpe.
Really?
Yeah, that's the official name.
Octothorpe?
Yeah.
So that's just related to 8 somehow.
Yeah, it's got 8 little points on it.
Oh, okay. Interesting. Okay. All right, let's just add to the confusion. All right. I spell it octa.
Oh, heavens. Give me a second. I'll
Okay. Okay. All right. So I'll just say proceed with. I'll just put the actual symbol in there. And as far as multi-line comments, you actually can see an example. Well, actually, there's both kind of comments here. In this py file, there's a pound sign for these single-line comments. And then multi-line comments, we have quotes, 3 double quotes on a line by itself to begin the multi-line comment, and then same thing on a line by itself to end it. Probably not. Okay.
And the spelling of Octothorpe.
Okay.
Octothorp.
Oh, this is good. Again?
Octothorp.
Okay. Okay. All right. All right. We're on record with that. All right. And then okay, multi-line comments. Actually, let's try it. Okay. So if I do, okay. I'm not sure actually. Oh. Yep. It has to be 3, because anything else will interpret as a string constant. So here it thinks I'm beginning a quoted string, and it gives me an error. 2 of them, 2 double quotes by itself would be interpreted as an empty quoted string. So 3 is interpreted as, so here is a multi-line comment. And then 3 more to end it. Okay. Okay. So I'll be putting single line comments for most part throughout this tutorial. Okay. All right. So getting help, kind of similar to what you do in Matlab. But just the syntax is a little different. So instead of doing like Python has a print command. Now, this is what you do in Matlab, help space print, but that does not work in Python. Whatever you want help on, you would put it, like whatever Python function or command, you would put in parentheses, and then it'll give you this short description. Another way to get help is using the question mark, followed by whatever it is you want. Oh, here I'm getting help on help. So, so question mark. Okay, so for instance, question mark print is what I really wanted to do, and that will print the same thing as what I did is using help parentheses print. Okay. But in Spider, there's also the help console. You can type anything up there and get help on it. I just closed that for the purpose of this tutorial. What's interesting is when I was putting my command, I put all my commands in this tutorial in a script over here, and would run them, and it would let me do help parentheses print. It would not honor the question mark syntax, so you cannot put that in a script. I mean, you probably wouldn't want to. But yeah, so that's one of the aggravating things about Python compared to Matlab. Actually, in Matlab, whatever you type at the prompt, you can dump it to an M file and run it, and everything works. But there's certain exceptions in Python. Whatever you type at the prompt, certain things cannot necessarily be typed in a .py file and expect to run. For the most part, you can. But yeah, I've encountered some gotchas there. Okay, to look at basically using your Python console as a desk calculator, like I often do with Matlab, and the syntax is largely the same. So I can work with variables and numeric constants and make assignments. But notice here, it doesn't, unlike Matlab, it does not print the result. Now what you can do is I can just type A at the prompt by itself, and it'll give me the value. Or you can, now that will not work though that's one of the exceptions. If I just type A here and run this script, it won't print it. So instead, if you're running a script file and you want it to print the value of a certain variable, use the print command, and that'll do it for you. Okay. Now, using standard mathematical functions. So let's suppose I want to take the square root of a. So b equals square root of a. Now this, what I've typed here, is the command that you would use in Matlab to do this. But if I try this now in Python, it's going to be like square root. I don't know what that is. So you have to make the square root function available to Python so that it knows what function to call. So I need to import the math package. So by default, there's only a few very fundamental packages that are preloaded. For example, the one that would contain print and certain other essential functions like that, but not math functions. So the way you import math is I can do import. So the simplest form is this: import math. And now all the functions in the math package are loaded, but to actually access them, I still can't do this. Not exactly. I do math.square root of a. And then there's the value of square root of 8 right there would be square root of 7.
Is there a way to like do a startup file that those packages need all the time so you don't have to?
Let's see. As far, because normally, yeah, like whatever scripts you're writing, you have a necessary, you put the necessary import statements in it. And actually, that's probably the best way to go because otherwise, you are. I imagine there's a facility where you can make sure that your own Python consoles will run something for you, but then you send your code to somebody else. And what you'll see in all the .py files that I'll write or you'll write during the semester, there's certain import statements you're just going to have naturally. Similar for other functions like exponential, math.exp, and like the trig functions, etc. Now, one thing I want to point out here is notice the how many decimal places. There's quite a few decimal places displayed. Well, actually, notice in both of these, the magnitude is different, but the total number of decimal places, either to the left or right of a decimal point, is the same. So 1, 2, 3, 4, 6, 7, 12. Looks like 17 places. Yeah. So 17 digits, significant digits total, are displayed. Now, you can actually adjust that. So at in the console, you can. So what I could do is I could say %sign precision, and let's suppose I want to have just 4 digits. Okay, so then it changes that. So now if I print the value of B, there's 4 decimal places there, and if I do C, so here, but now it's a fixed number of decimal places. So it's similar to, not exactly, but similar to Matlab's like format short, for instance. And if I want to restore the default behavior of how it prints numbers, use precision again with no argument. So then it goes back to the way it was. Okay. Now, other central operations like multiplication and division work exactly the same as in MATLAB, you're using a asterisk over the slash. However, exponentiation is different. This is actually the operator for exponentiation that was used way back in the original Fortran. Use 2 asterisks, not the up arrow. So I would say, for instance, A equals B squared. B was computed earlier to square root of 7. So use the double star for squaring. Okay. Yeah, so that's one common gotcha there. And there's certain other central operations like and or and so forth that are a little bit different than how you would do them in MATLAB, but maybe more similar to other programming languages. Okay. Well, let's take our first break here, and then we'll pick up again at noon to continue. Okay. Well, since I was doing a break took longer than expected, and we all start late, so okay, everybody's still here. You'd moved. Oh, okay. So we'll just go straight until the end time of 1:15 instead of having a second break. Okay. Now, so one thing I was pointing out during a break. Now with Matlab, you can then state with a semicolon or not. It's your choice. If there's a semicolon, it won't print. If there's no semicolon, it will. The default really in Python is simply not to print, but semicolon still has a use for if you want to have multiple statements on the same line. So, for example, if I have like d equals 2 times b, semicolon f equals d squared. So recall that b was the square root of 7, and then d, sure enough, is twice that, and then f is that whole thing squared. So, of course, twice the square root of 7 squared would end up being 28. So that's one good to know thing there. Now that we know how to use certain standard mathematical functions and also perform arithmetic operations, including exponentiation, which is a little different from Matlab. So to make sure that you're on board with syntax of mathematical expressions in Python. Okay. There's only an hour left. Okay, so this is an exercise that was originally given in Matlab, but we're going to do the same kind of thing in Python. So what I'd like you guys to type in at the prompt is to set the variables a, b, and c equal to these values, 1, -5, and 6. I'll go ahead and do the same. Okay. And if we want the roots of the quadratic equation, ax squared plus bx plus c equals 0, or in this case, it's x squared minus 5x plus 6 is equals 0. Now, this is one that, of course, is easily factorable. So, especially since, well, all of you, sorry, you haven't worked in the zone per se, right? Or you do now? In the summer, yeah. Okay. So you all work in the zone, or you're about to. Okay. So all this has to be very much second nature. But what I like you guys to do in Python, though, is since you know what can figure out what the roots are going to be in your head, so you know what they're supposed to be, is if you type, like for x1 and x2 will be the two roots. So type out the quadratic formula using proper Python syntax and also function references, or the one that you would need for a quadratic formula, and make sure that you actually get the values that you would expect. So I'm not going to type it out right here yet. Make sure that, well, the 5 of you in this room can do it. So basically you're completing this line, and you're using whatever parentheses, etc., for the quadratic formula using a, b, and c. So not strict numbers 1, -5, and 6, but so literally minus b plus or minus. Well, for x1, choose the plus sign, and then after that, same thing for x2 with the minus sign. So if you get the numbers you expect, great. If there's some syntax error, we're not sure how to proceed, let me know. So at least we'll have 5 of you squared away. So if you're doing this from home, I will put up your correct expression after, so you might want to pause the video. Anyone still working? Well, well, the first was A, B, and C. So, if I space up equals, actually use that. Okay. So, you think about, I just type out quadratic formula, but here you need to have the right parentheses with the expression in the numerator. So you literally type out with appropriate parentheses. Minus b plus square root of. Yeah. All set. Okay. Right, but keep in mind that since the whole thing, whole numerator will be divided by 2a, keep in mind parentheses. Yeah. Okay. Yeah. But yeah, that's a correct function usage.
You need to type import math before you
Oh,
math.
yes, you do. Oh, you didn't do it earlier. Okay,
I did it earlier, but
yeah, yeah. In every console session. So once you've imported it once in that console session, you don't have to do it again.
okay.
Yeah. Did you get it? Okay. Oh, exponentiation. The b squared. That has to be done. Use the up arrow. Up arrow. Is it the up So yeah, so the expression would be minus b, and we use a plus sign, plus math dot square root b squared, with that syntax, minus 4ac over 2a. Well, divided by 2 will work in this case because a is equal to 1. And then x1 is the larger root of 3. And then you can just switch to the minus sign. Whoops, I didn't want to do that. Hold on. x2 is what I want to call that one. Okay, that's a smaller root of 2. Okay. Oh, whoops. All right. Okay. Now, let's see. Now, the other part of this exercise. Okay. So here we have a Gaussian function. So 1 over square root of 2 pi. Let me make it a little bigger. E to the minus 1/2 x squared. So what I'd like you guys to do is, if you let x equal to, let's go with x equal a, because we already have a value of a defined. A is equal to 1. If we go ahead and fill in this expression. Now, as far as pi is concerned, so pi is predefined as a constant in Python. So, okay, I'll type out the problem here. Evaluate 1 over square root of 2 pi times e to the minus 1/2 x squared. So this is actually how I would type it out if this was in Matlab. At x equals 1. So you could, well, at x equals a, because we already have a value for a. Now, you could do math.pi, and so that constant is predefined. The floating point representation of pi. So the idea is you can use this math.pi here in this expression. And I'm going to cheat here by evaluating the same expression in Matlab. Oh. Oh, it didn't like when I pasted the space, or something didn't translate well. I'll set x equal 1. Okay, so all right, so roughly point 0.24197. Okay, so should get approximately 24. All right, just that's how you know you're doing it correctly. So EXP, you'll have to treat the same way as you did square root. Okay. Anybody having difficulty? And from the MATLAB-like statement I typed in, you can see at least what parentheses you need. It's just that certain things, parts have to be written in Python syntax or references instead.
Is there a way to not have to type that out?
Yes, I'm coming to that next. Okay. Yeah, it is a pain, isn't it? Okay.
Well, it's whole 5 characters.
But per occurrence.
Well, yeah. Any n taken to an arbitrarily large power.
Yep. Maybe if I change like it of a text to light. Okay, referring to this.
Yeah.
Let me see if I can change the color. Here we go. Syntax coloring. Okay. Okay. All right, for a comment. Wait. That's strange. It wouldn't change the color.
There is another option. Maybe we can change the contrast on the projector.
Okay. It's weird. I'm changing the coloring scheme, and it refuses to honor those changes. That's a bug. Okay. Maybe if I hit. Man, it's aggravating. Oh, okay. That time it did. I'm not sure why I didn't do anything different. Oh. Oh, it wiped out my stuff. You bastard. Okay, that's okay. All right. If I go, yeah. So panes is where you can view what you've done. So here are all the commands that I've run today. Okay. So what I'm going to do, I'll show it. Okay. I mean, it's one thing to open a new console. That's fine. I don't really care about that. Oh, it's interesting. Okay, so because it's the command is on command number 57. Okay, but I'm gonna go to this console. Okay, and oh, right, the first command I typed in was invalid. Okay, so if I go back to the history log and copy everything I did today except for the first line. Ugh, yeah, that's very bad behavior on its part. Okay. Wait. Where did my console go? Okay. Man, it's aggravating. Okay. So those are all my commands. Okay.
Do you have to do the recall?
Well, I did at the start, but I think it got through. Yeah, but it's really treating us all as one command, so that's really not going to be the same thing. Okay. Yeah, it really aggravates me that I totally redid my consoles like that. So at least all my commands are there. I'm not sure how I'm going to handle that, because at least for what I post later today, I'll have my history log, so I can post that. Okay. Now, okay, so where were we? First was this is what I want you guys to do. Okay, so anybody still need to do that? So what you're going to do is that's your expression, except instead of these things will work in Python. This is Matlab syntax. So square root, exp, exponentiation, pi, all to be done differently. All right, so please get that done quickly. And if you have any trouble, please ask me immediately. Lost enough time on this whole coloring crap. Yep. Okay. Oh, I'll put out the statement I got earlier. That's the value you're supposed to get. Something close to that. Yeah, but you won't need any parentheses other than what I already put there. Make sure to do exponentiation Python's way, not Matlab's. You know, similar to that, for how squaring is done. Got it? Okay, so yeah, so the expression is 1 over math dot square root 2 times math dot pi times math dot exp minus 1/2 times x squared. Oh, I didn't have a value for x. I'll use a. A is equal to 1. Yeah. Okay. Now, but yeah, that's a lot of math dot, math dot, math dot. Let's not do that if we don't have to. So this leads to another usage of the import command, because before I did, so it can import individual functions from packages. So how I could do that, for instance, if there's only particular ones that you need, I could say from math import square root. And I can do that with the other symbols that I used, exp and pi. And you could do one, so now I can do this, 1 over square root 2 pi. So this is closer to the Matlab syntax, except for the exponentiation. And that all works. But in a way, this kind of replaces one kind of tedium with another, because now you're doing a whole bunch of import statements for every function you might need. Now, because here's what you could do instead. I can choose to import everything. Okay, so now certain functions that to this point I've not yet used, like sine, I can now do. Now, this leads to a natural question of why not always do that? So use import star carefully. What about name conflicts? What if you are importing from multiple packages, and some of these packages have the same same function name, same symbol for entirely different purposes? Well, the last so there's an ambiguity that's created, and you may not be sure which one you're using. Now, what you could do is you can resolve that ambiguity yourself by saying, like, if exp is a symbol in multiple packages, you want to use the math one, you could say math.exp, and that'll resolve the ambiguity. So you can always go back to that. But yeah, so name conflicts are a legitimate issue. And in fact, I can show you, look at the documentation for SciPy and NumPy. If I go to the documentation for NumPy, for instance, if I look at the index, and there are various symbols, like, okay, here's, I'll just pick one at random. Argsort is a symbol that's defined in every single one of these submodules of or packages of NumPy. So a lot of potential ambiguity there. So it's not an uncommon thing to have that happen. Okay.
How do we know what packages we can import these from?
Yeah. That's yeah. So unfortunately, um, when you're just trying to pick this up first time, especially when you're making a transition from Matlab, what I found myself doing often preparing materials is that I would even Google, how do I do this Matlab thing in Python? And apparently there are zillions of message boards where people are asking exactly that question. How do I do this Matlab thing in Python? And like if it's something that's a scientific computing function, it's something that seems like it's likely to be in NumPy or SciPy or one of those packages, then at least you have its documentation you can search. But for some things that are more obscure, um, you also have to dig yourself, unfortunately, because it's not always clear what's out there.
Well, I mean, like, okay, the math package, obviously, looking at math, what other packages are out there? You know, like, is there a graphics package, a printing package, within, that's my question.
Okay.
Categories of packages might you want to know?
Oh, well, so in this class, there are just certain standard ones that we're going to use. For example, there's a separate plotting package, Matplotlib, and I'm going to show you that. So for everything that I've had in mind for you guys to do in this class so far, it's been sufficient to work with math, NumPy, sometimes a sub-package of NumPy. And we'll come to that. Like, for instance, there's NumPy. Okay, so I'll type these here. Okay, so NumPy.linalg. I need to use that because there'll be a method that's defined in linalg, but not the top level NumPy. SciPy and subpackages, which can all be listed in documentation, and of course math, of course, Matplotlib, but not the top level package. There's a sub package of that called pyplot. So that had the actual plotting functionality that I needed. So you'll see me importing these things as I need them. And if I flip back to the NumPy SciPy documentation, you'll see, like, for instance, if you're looking for a particular kind of thing, like for like solving a linear system or whatever, it'll show you here in the index which sub package is listed under. So at least that documentation is. So if you think that something's in NumPy, but you're not sure where, this documentation can help you locate it.
And if you use a command that's not loaded, does it tell you, hey, you need to load this package that it's in, or does it just do nothing?
It'll tell you that the symbol's not defined, but it won't help you find it. Yeah. Okay. Yeah, so that's one of the difficulties with all this open sourceness, is that there's help out there, but it's not as structured as you'd like it to be. Unlike Matlab, for instance, where there's one place you can go and literally all the info is there. Okay. Now, all right, I have a little less than half an hour. Let's deal with some basic matrix operations. Okay. So for that, I need NumPy for the first time today. So this is something I'll be doing often, import NumPy. Now, if I just do that, then I'm typing NumPy dot all over the place. But you don't have to do that, especially you wouldn't want to do that if it's like a really long package name. you can abbreviate. You can make up your own abbreviations for what you import. So I can say import NumPy as NP.
So it's like an alias.
Yes. And I found that particularly useful really for plotting, because for plotting, I have to import this, matplotlib.pyplot. I don't want to type that all the time. So I could give that an abbreviation. I imported it, or will later, as like PLT. So I could say PLT dot from this point on. Okay, so now I'll be using like NP dot at various places. So what I'm going to do here is I'm going to type in a comment like this one. I'm going to type in a Matlab command, Matlab syntax, and then I'll type for real, so uncommented, the actual Python command that will carry out the Matlab task, just so you can make that association. So what I'm going to do is I want to create a 2x2 matrix. So how I would do that in Matlab, I could do like 1, 0, semicolon, 0, 2. This is a diagonal matrix. So how I do this same thing in Python, I could say A equals np.array. So that is a function or method that Python uses to create a matrix with given entries. So, and the way I create a matrix with a given entries, like it's 1, 0, 0, 2, is it's a list of lists. So Python, you're using lists all the time. And the way lists are prescribed in Python is you start it with a square bracket, and then the elements of a list are separated by commas. So this square bracket starts the matrix. Now, these spaces I'm putting in, you don't have to put them in. I'm just putting them in so it's easier to see. So now I begin the first row. So I do 1, 0. So the first row is a list, a Python list of 2 elements, a 1 and then a 0. And then that row is the first element of the list that describes the matrix. So now I put a comma, and now I do another list for the second row, 0, 2. And then I end that, and then I close the parentheses. And that's my whole command. So the outer square brackets describe a list that has 2 elements, the 2 rows. Each one of those rows is itself a list. So that's why I describe it as a list of lists. And then if I want to print out A, the output shows me it's an array. So this is what is referred to as a ND array. That's the actual type name. You may not use that terminology in your code, but that's what the type is called. So that can be used to describe any dimension array, a vector, a matrix, a tensor, like a 3, 4, or any dimensional array you want. So you just have your lists nested that deep. So any questions about how this kind of matrix is created? I'll do another, just so I can have 2 matrices to work with. So B will be a matrix 5, 7, 9, 10. So that's the Matlab command. So in Python, do np array, square bracket to start the matrix, and then first row, 5, 7, comma, then second row, 9, 10. All right, so again, a list of lists. And once you've done that, you can perform matrix arithmetic. Now, the simplest operations, addition, subtraction, scalar multiplication, that's exactly the same as in Matlab. So I can do like C equals A plus B. And that sums these 2 matrices. Or I could do scalar multiplication, like 4 times a. So all of that, subtraction also, all of that works as expected. So addition, subtraction, scalar multiplication. And I'm emphasizing scalar multiplication as opposed to matrix multiplication, because that does not work the same way. Okay. So what I'm going to do to demonstrate what's different for matrix multiplication is I'm going to go over to Matlab. I'll need to make this font bigger, a lot bigger. Okay, fonts. Say. Okay, I'm going to create the same matrices. So in fact, I can copy and paste the same commands that I had commented out before. Oh, yeah, there's something about pasting from Python console into Matlab. There's some extra character that goes with it that it doesn't like. So if I backspace over it, okay, then it works. Okay, so those are the same A and B in Matlab and Python. I'm going to make this a little smaller so you can see both. Okay. Oh, I don't want this. Okay. Let's adjust this too. Okay. Now, over here in Matlab, I'm going to do A times B. As you know, that does matrix multiplication in Matlab. So 5, 7, 18, 20. All right. Now, 5, 7, 18, 20 is what we got for A times B. Let's do the same command, A times B, in Python. Well, actually, first, I'm going to bring the matrices back, just so we can have them in front of us, A and B. And now, I'll do A times B. Not even close. 5, 0, 0, 20. Now, so it obviously did not perform matrix multiplication, which is supposed to be 5, 7, 18, 20. So looking at the matrices that you had, 1, 0, 0, 2, and then 5, 7, 9, 10, and A times B being 5, 0, 0, 20, can anyone think of, since it obviously didn't perform matrix multiplication, what operation do you think it might have done instead? What? Yes. So in Python, A times B is element-wise. Exactly that. As A dot star B in Matlab. Okay. Seems a little inconvenient. When doing linear algebra operations, if you're going to multiply two matrices, chances are you really want matrix multiplication rather than component-wise. It seems like a rather annoying choice of default. Although I believe the other, but this is an array type, not a matrix type. So I believe Python's matrix type, A times B really would be matrix multiplication, but we're not using that one here. Now, fortunately, it's not difficult to perform matrix multiplication in Python using NumPy's ND arrays. I can do C is equal to NP dot, and then the function name is dot. And that will do the job. So dot AB, assuming the matrices have the correct dimensions for matrix multiplication, it will compute the matrix product. Can anyone think of why it's called dot? Why does that name make sense here? It does refer to dot product, How does the dot product relate to matrix multiplication? It's something I talk about in 610. But no one has taken that recently, or haven't taken it at all. It's because an entry of a matrix, the ij entry of a product is equal to the dot product of row I of A with column j of B. So every entry of a matrix product is itself a dot product. So what it's doing is it's doing all possible dot products of rows of A with columns of B. Okay. Now, so far we've only looked at matrices. What about vectors? I can create a vector. Now that's just, if I want a row vector, so I'll make it np.array. But here I just need one list, not a list of lists. So I could say like 4, 5, 6. So that gives me a row vector. Now, what's nice about Python is that a lot of operations that require a vector, it doesn't really matter if you make it a row or column vector. It'll take it and work with it. For example, ax equals b, which we'll come to later. You can define b this way, and you might think, oh, it's a row vector, but shouldn't it be a column vector? But its function for solving systems, it'll take b in whatever form. It'll work with it. So it's a little more flexible that way. If I really want it to be a column vector, though, I can do that too, where I can say each element is a row. So now it is a list of lists again. It's just that for rows, the lists representing the rows only have one element each. So notice the difference in syntax. There's an extra layer of square brackets. So if I have it print what W is, it actually displays it as a column vector. Most times you don't need to do this. You can just work with the first form, and that's probably enough for your purposes because you can access its elements and everything works the way that it should. Now, as far as accessing elements, I didn't try this earlier, but I want to try it now in front of you guys. How you access elements is different between MATLAB and Python. MATLAB indexing is one-based. In other words, if I want to access the first element, of a vector, I could say like x1, and that's how it works in your code. So first element is w1, a vector I just created here, and they use parentheses. Python indexing is zero-based, like other languages, like C and C++, for instance. So first element is w square bracket 0. Now I want to try this with this here. Okay. Oh, it gives me the first element as an array. But I want the actual number. So if I do row 0, column 0, in other words, first row, first column, then it gives me a 4. Whereas if I go back to the other form of creating a row vector, I want the first element, then it just gives me the number. So generally, this is what you'd want to do if you're creating vectors. Just make it a one-dimensional array. That makes element access easier. What about a matrix? Here's my matrix C, for instance. If I want the first row, first column, I can do that. And similar to MATLAB sequence where syntax where you do I, comma, j, but Python is in square brackets versus parentheses in MATLAB. Okay, so this would be the second row, first column, which is the 18. You can also use this syntax. C sub 1 is the second row, and then it takes the first element of that. So that's an alternative syntax. It's not identical though. I would recommend I would recommend using this syntax to access individual matrix entries instead of this one. There were some cases, unfortunately, I can't remember off the top of my head right now, where this second syntax caused some unexpected behavior.
Can you reference an entire row or entire column by using like a colon or something like that?
Yes, you can, and that's something we'll come to. Actually, you know what? That's a situation I was trying to remember. When you're trying to do those kind of references to extract like an entire row or column or whatever, using this first syntax is much better for that than the other one. Okay. All right. Actually, I think what I'll do is... Yeah, I'll get to this part later. Okay, I have a section on complex numbers and such, which I do want to do, but not yet. Okay. Okay. Creating special vectors and matrices. Now, there are certain Matlab functions you're familiar with that create matrices of interest. Like, for instance, what if you need a zero matrix of a certain size, or a matrix of all ones, or a random matrix? So you can do all those things in Python too. So if I continue, here's a Matlab command. I want like a 6x5 matrix of all ones. How you do that in Python is np.ones. It's the same function name. But be careful with the arguments. Notice I put the 6 and the 5 in parentheses. And then that is passed as the argument to ones. So that gives me a 6x5 matrix of all ones. Now, the reason for that is, so the ordered pair is referred to as a shape. In other words, it's indicating dimensions of a matrix or other kind of n-dimensional array. And in fact, I can do e.shape, and that gives me this ordered pair, indicating number of rows, number of columns. So e.shape is equivalent of MATLAB's size of e, and that both of them return a list or array of two elements, the first indicating a number of rows, the second indicating a number of columns. Okay. Now, you can also pass, like if I want a vector, a row vector of ones, I can do that. Oh, whoops. I forgot the NP. And that gives me a row vector of ones. Now, here's where you have to be careful. One argument to ones gives you a row vector, as I just showed you. If I do this kind of command in MATLAB, ones with only one argument, it does not do that. Does anyone remember what that does do? If I have ones, three, if I do this, like what I've highlighted here, if I do this in MATLAB, it's not going to give me a row vector of 3 elements. Yeah, it assumes square matrix. So that behavior is very different, so be careful about that. So as opposed to MATLAB's square matrix. Okay, so that's one key difference. The other thing I want to point out here is notice it says it's not just 1, 1, 1. It's 1 dot, 1 dot, 1 dot. So 1 dot is a floating point number. 1 without the dots is an integer. So that's one thing to be careful about. In MATLAB, all numbers by default are floating point numbers. You can force things to be an integer for various purposes, or you can always convert back and forth. Python, you can also convert back and forth, but if you specify numeric constant that's an integer, it'll type it as an integer. What you might want to do is force it to be a floating point number using the dot, because otherwise you get some strange things happening. Like I had some unexpected problems because it was performing integer arithmetic rather than floating point arithmetic, and those are different operations.
Did you specify 1 dot, or did you just specify ones?
Yeah, so ones, this function will produce floating point. Although, if I were to look, actually, this would be a good time to consult the documentation, because, okay, I'm going to look up a function ones. Okay, here we go. I'll make this bigger. Okay, here's the function ones. And here's a shape, that's what I specified. And here there's optional arguments, d-type, and then order. D-type by default is float 64, an 8-byte floating double precision floating point number, which is what we're used to. However, if you really want an array full of ones that's of integers, you can specify different type. So like numpy.int8 is a 1-byte integer, for example. And then the order, that's for storage purposes, storage in memory, because there are different conventions for storing arrays, using like a Fortran convention where it's by column, or a C convention by row, and you can choose. But the default is the C convention, storing by row. So as an example, I'm going to try this now. I want to create an array of 3 ones like before, but I want to force them to be 32-bit integers. D-type int 32. Let's see if it'll take that. Oh, it doesn't like. Wait, maybe I need to put in quotes. Yes, I need to put in quotes. Notice the dots are gone. And it indicates this is the data type because it's different than the default. Okay. So if you really want integers in this situation, you can get them. Okay. All right. There's also a zeros function that works in the same way. np.zeros. So if I want like a 3x4 matrix, so that's the same as the Matlab syntax. Just need the np dot and also the extra layer of parentheses for a matrix. Or I can do so again with 1 argument, that will create a row vector. So that's the MATLAB equivalent there. Okay, you can also create a random matrix, but here you need to go to a sub package. So I can't do rand, I gotta do np.random.rand. And here you don't need the extra parentheses. It expects rows and columns as separate arguments. So there's the MATLAB equivalent there. And it's just like in MATLAB, random entries are uniformly distributed in the interval 0 to 1. Okay. Okay. So I want a random matrix with entries in -1 to 1. So what I can do is I can make a random matrix of a size I want, so 3 by 2, and then I will scale it by 2. So now those entries will be distributed between 0 and 2, and then I can say -1 to shift them all so that they are distributed between -1 and 1 as these are. So another similarity with Matlab. Okay, so if you have a matrix and you want to add or subtract some scalar to it, it knows what you mean, that you want to carry out that operation for all entries of a matrix. So it treats it, so it makes this 1 here into a matrix of all ones that's the same size as this one to perform the operation. So you don't so it handles that in a non-cumbersome way. Okay. All right. Well, just about out of time. Plenty more to get through, but that's what we can continue on Thursday. So, yeah, for example, accessing entries, rows, and columns, extracting submatrices, or other uses of a colon operator, like to create ranges of numbers, things like that. Well, and a whole lot more. So, okay. But yeah, it looks like I have my work cut out for me to. Yeah, unfortunately, the output for my first session is lost, but I have the commands. So I'll post something. Well, I'll also post this video for sure. Okay. So if I'm not hauled into court, I'll see you Thursday. Or any last questions while I'm still taping? Okay.